this was defined as C minus A, D minus B, C minus B, D minus A. Yeah? These are all lengths of certain line segments with a sign. Can be negative. These angles, you have to be directed. If you want to get the correct sign, then you have to be careful. For example, counterclockwise angles have a positive sign and so on, things like that. How can we make a link between these angles, the signs of these angles, and the lengths of these line segments? In Euclidean geometry, any idea? So if we want to prove that this, our definition, is the same as this, we have to make a link between the size of these angles and the length of these line segments, which is here. How can we make a link between them? Crossbar, no, that's not numeric. You can use the sine rule, for example, the rule of sines. Or you can, what you can do, the most beautiful way is, here you are talking about ratios of line segments. The ratio of these two line segments, for example, is the same as the ratio of these two areas because they have the same height. So you can translate this in terms of areas of triangles with vertex at P. See? Okay. So let's reinterpret this as areas. This is the area of the triangle CPA, area of the triangle DPB, and so on. And now we have to get a relation between the area of APB, for example, and the sine of this angle. How do we do that? If you have an angle, then the area is 1/2 times the one side, the other side, and the sine in between. You do that, you get a complicated formula where all these lengths also appear, but they all cancel out. That's a beautiful thing. And the only thing you keep is this. So that's another proof that this cross ratio is the same here and here, because the situation here, the angles are the same. Yeah? Okay. Yeah.
You shift from conic to circle.
Yeah.
And so you have a projective plane and you have R2.
Yeah. That's choice of suitable line of infinity. Yeah.
So the projective would be 3 and then it becomes R2.
When I go from P2 to R2, I always choose a suitable line of infinity. But here I argued a bit quicker. I just said, well, I don't really care where this line of infinity is because I don't need special things about parallel lines or so. The only thing I used was, in projective geometry, all conics are equivalent. So I can assume it's this conic. Yeah? All conics are equivalent, so I can assume it's this conic. And now I choose z is 0 as the line of infinity, and then I get the standard circle. That's what I did. Yeah. Okay. Right. Cover this. Duality. Let's look at Pappos theorem. Let's dualize Pappos theorem. Okay? I will start GeoGebra. Pappos. Pappos was given two distinct lines. That was the start, wasn't it? Yes. So, what's the dual of that? Given two distinct points. How shall we call them?
L and M.
L and M?
Lines L and line M, so what is the Pappos?
So given two, in original Pappos, given two distinct lines, lowercase l, lowercase m, dually given two distinct points, capital L, capital M. Okay, what was the next thing we did in Papa's theorem?
Distinct points. P1, 2, 3.
Yeah, exactly. 3 distinct points on the line L. What's the dual of that statement?
Lines.
Exactly.
Through
Okay, and we have to give them names.
B1, B2,
Lowercase p1, lowercase p2. These are names of the lines. Lowercase p3, good, 3. And similar, of course, here. Oops. The dual of Papa's is pretty messy, so it's true. Q1, rename Q2, rename Q3. Okay. So given this, these points here, they do not really matter. I only use them to define the lines. And I like to keep them because later I can move them around to get a nicer picture where we can see more things happening. Yeah? Okay, what's the next thing we did in Papa's? Join points P1 and Q2. So draw the line connecting P1 and Q2. What's the dual of that?
section points of
Exactly.
P1 and Q2.
We take the intersection point of P1 and Q2. And I think we call, yeah, so at this point we call capital S12. Yeah? No.
We don't.
No, you're right.
It's the
How do we
line
call
between
this?
the other ones.
P1, Q2?
It's always safe.
Very nice name anyway.
Oh, yeah. Beautiful name. It looks like a chicken disease. P1, Q3?
So I guess it's the
No,
name of a
no.
Star Wars robot.
We have P1, now we should take P2, Q1.
Yeah.
P2, Q1. This one? Yeah. P2, Q1. That's really a virus. Yeah. Okay. And then we took the line joining these. Oh dear. What did we
The
do?
intersection point of the
Yeah, we took
original
the intersection
lines.
point. So what's the dual?
S1, 2.
The line joining these two. So now we take the line joining this point and this point.
It's
And-
called S1.
And this is lowercase s12. Yeah, dan moet ik denk ik zo doen. So this line is dual to the point capital S12 in Papa's. Yeah? Okay, now we continue. P1, Q3. Where is it? Here it is. I think it's Q. Yeah. And we call this P1, Q3. And P3, Q1. P3, Q1. And we join those two. And we call that S, oops, lowercase 13. Okay. And finally, 2 and 3, P2, Q3, P2, Q3, and P3, Q2,
Yeah.
P3, Q2, P3, oh, Q2. And now we join the two, this one and this one, and that is S lowercase 23. Yeah? Okay, so we have now constructed the three lines, S1, Sij, dual to the intersection points capital Sij. What was the Pappus statement? These 3 points lie on the line. What's the dual statement?
These 3 lines is consecutive.
These 3 lines pass through a single point, are concurrent. So let's define the intersection of S12 and S13, and then check whether this point lies on S23. Okay? So I'm going to define the intersection of S12 and S13. And let's call this the point. Well, let's see. Yeah. Let's call this point Pappus. Pappus point. And now we have to check. Ooh, this looks good. Now we have to check whether the line S23 passes through this point. Yeah? So let's make this line red. Oh. Color, red, style.
Like a dick.
And make it the process always through. And it's also on the line LM. But that's, well,
That's a coincidence.
yeah, that's right.
So let's check.
When I do it at home,
Because the dual thing is false. Oh no, it's almost true.
Yeah, you see, things that I'm the same at home as well.
So this is the advantage of GeoGebra. You can check. Yeah. So this is the dual of Pappus. Yeah. Good. Great. Okay. So one thing we didn't do, which is great fun, but unfortunately we didn't have the time, is the dual of a conic. We know the dual of a point, the dual of a line. We do not know what the dual of a conic is. It's the conic itself. But it's not part of the exam. Okay. Let's probably this. A couple of you, hyperbolic parallel axiom. Yeah. This question. Yeah? Okay. In the first 6 lectures of the lecture series, we looked at Euclidean geometry from an axiomatic point of view and also from a coordinate point of view. And we looked at how the two are related. Okay. I could do that because Euclidean geometry itself is familiar. Yeah? So we just took the familiar geometry and had a deeper, we made a deeper study of that subject, school geometry. Projective geometry, I suppose, is new to most students. So projective geometry itself was to get to know a bit of projective geometry itself was the main goal of the second lecture series. In particular, the relation with R2. Yeah. Okay. So we only we didn't think about other fields. We always looked only we only computed about real numbers, worked over the real numbers, and we didn't try to approach projective geometry axiomatically. You know, we only looked at it from the coordinate point of view. From the model, we have a certain model of projective geometry, and we work in that model. Okay. I didn't pay much attention or any attention to the axioms in projective geometry. In fact, Stilwell has a different approach. He is interested in the axiomatic approach to projective geometry. We know, for example, that you can characterize the Euclidean real plane, R2, by all these axioms in Stilwell, including the Dedekind axiom. That's important. The Dedekind axiom gives you the real numbers. There are similar systems of axioms characterizing the projective plane. The real